So I'm very happy and honored to be here to give my talk. I wish I could be actually in Seoul in person, but I have when I got this invitation, I already have agreed to go to a conference in Madrid. So actually, I'm flying out to Madrid tomorrow. So that made it difficult to me. But thank you for accommodating my schedule by allowing me to speak online. So, the thing that I would like to tell you about is the following. So since, for example, when we learn quantum mechanics in undergraduate, one of the things that we do is that when the system has symmetry, it's useful to decompose the energy eigenstate into irreducible representation of the symmetry. So the same in quantum field theory. So if quantum field theory has global symmetry, it's useful to understand how its energy eigenstates are decomposed into irreducible representation. And so today I'd like to point out that in fact for CFT and in fact for that matter for any quantum field theory, unitary relativistic quantum field theory, there is a universal behavior of how the Hilbert space gets decomposed into irreducible representation in the limit of high energy or high temperature. So I'd like to exhibit some rather fairly universal pattern for both continuous symmetry and discrete symmetry, and also mention my recent work on similar decomposition for entanglement entropy and the entanglement spectra. And I would also like to mention some of property of correlation function in similar limit. So specifically, I will discuss high energy asymptotic behavior of density of states and three-point function of conformal field theory. But since any unitary relativistic quantum field theory becomes conformal field theory in the high energy limit, you can think of this result applicable to any of such quantum field theory. So this is actually based on a series of papers that I have been writing during the pandemic. And so this was one of my pandemic projects. And so I'd like to thank all my collaborators for this work. So let me begin. So suppose you have unitary quantum field theory in D space-time dimensions. For the purpose of this presentation, D is a dimension of both space and time. And suppose I calculated this thermal free energy. And so then if we go to high temperature limit, and supposing that we have large but fixed volume Cauchy surface. So suppose the space Cauchy surface is compact like D minus one dimensional sphere. And so then, so high energy limit, we should have some kind of leading behavior must have thermodynamic property. And but since this is conformal, so this has to be dimensionless. So thermodynamic property means in particular that free energy should be extensive. So that means it should scale like a volume of the Cauchy surface. And so that has the length dimension D to D minus one. But that means that it should be compensated by proper power of the temperature. So that fixes the coefficient. And the unitarity demands that this coefficient F is positive. So you have some universal, some positive number associated to each theory. So F is a theory-dependent quantity. So for example, in 2 dimensions, this F is related to the central charge of the Virasoro algebra, and this is the celebrated Cardi formula. So basically what I would like to do for the remainder of time is to refine this formula. So this is just we are taking trace, but if the theory has global symmetry, there is a group action on the Hilbert space. So then if you can consider, for example, inserting unitary operators that implement the symmetry, but that means that this becomes a group dependent function. But it's actually a class function because it's be invariant under conjugation. And so then you can decompose into sum of characters. This is what I'm going to do later. And so then this allows us to decompose this formula into representations. So the question I would like to pose first is how the high energy Hilbert space in the limit of large temperature decomposes into irreducible representation of global and space-time symmetries. And then we'd like to do similar thing for correlation functions too. So, so I have structured my talk in the following way. So I'm going to present a bunch of results. So I'm going to show you many formulas answering this question. So since there are lots of formulas and lots of results, so things get a little bit confusing. So what I would like to do is first tell you all the results I would like to tell you about. And then, so that's going to be like first 15 minutes or so. And then in remainder of time, I would like to explain how we have arrived at those results. So if you hear the first part of my talk and found it interesting, please continue on to hear how we have arrived at those results. Okay, so that's how this talk is going to be structured. So first result is when the conformal field theory has finite group global symmetry. Okay, so in that case, the result is the following. So supposing instead of this partition function, consider some kind of twisted partition function where we insert a unitary operator associated to the group G. So for each group element, there is a neta current, neta charge. In the case of conformal field theory, quantum theory, it's a unitary operator associated to G. So you can consider inserting it and calculate this. And as I said, this is a class function, which means that it is invariant under conjugation of G. And in the limit of large temperature, namely beta goes to 0, I claim that this goes to delta function in the group, in this case, finite group. So it's you got 1 when G equal 1, and it's 0 otherwise in this limit. Okay, and we can decompose this into characters, and then from that, we can actually deduce this result. So in particular, if you consider asymptotic density of state, so delta is a conformal dimension, and R is an irreducible representation, in the limit of large delta, then we find that it is actually proportional to dimension square of the representation. Okay, so this is actually related to the Planck density of the group decomposition. And so you can see that if you sum this for all the unitary representation, there is a finite number of unitary representation, then this actually sums up to 1. So this is consistent. Okay. So this is what actually Daniel Harrow and I conjectured for any dimensions. But then after we, toward the end of the writing our paper, we realized that a year before, Shurdeep Pal and Jendi Sun actually obtained that formula in the case of 2 dimensions. In 2 dimensions, you can do the modular transformation trick. So you can actually arrive at this result fairly straightforwardly. And then I'm going to explain you how you arrive at similar result for higher dimensions. Okay, so this is the result for finite group. So then you can ask, well, how this can be generalized to continuous group. So naively, there are some difficulties, and we can imagine that we need a regularization for the following reasons, 2 reasons. One is that this denominator here is actually the number of elements of the group. And of course, if you have a continuous group, then there are continuously many elements. And also, there are infinitely many representations of the group. So if we try to sum all the representation, this numerator becomes infinite too. So in some sense, you have infinite over infinite in the case of a continuous group. So what's going to happen? So this is what we figured out last year with Monica Khan, who was a postdoc at CALTECH, and Jai Hari, who is my excellent graduate student, and actually the alumnus of Seoul National University. And so this is what we obtained. So if you do the same calculation inserting group element, then you can decompose into character. And then, in fact, just like before, you have a factor which is proportional to dimension. And if you turn this into density, it becomes dimension square. But then it's actually suppressed by the exponential of the second Casimir of the representation. So this is this regularization factor. So for example, if you do the Taylor Laplace transform of this result, we arrived at this result where the density of state in large conformal dimension and representation is again proportional to dimension square of the dimension of the representation squared, just like before. But then there is this regularization factor. So what this factor does is the following. So if you fix the representation and then take delta to be large, then this is going to become 1. So basically, the result is the same as the finite group case, where the probability is of finding high. So this is, you can think of this as a probability. So supposing you pick an arbitrary high energy state in the conformal field theory. What's the probability of finding that state in a particular irreducible representation? So this formula in the case of finite group says that it's proportional to the square of the dimension. And here again, if you fix the representation and then takes the energy to be large, then this becomes 1, so it's proportional to dimension square. That this formula says. But it cannot be dimension square for all the representation because there are infinitely many representations. So in fact, what's going to happen is that if you fix delta to be large but finite, and then take the representation to be large, then there is this exponential suppression by the second Cauchy. Okay, so this is what this formula says. So I'm going to derive this later. Edward, do you have a question?
Yeah, have you told us what B and B prime are?
Oh yes, I forgot to say what B and B prime. So just like F over here, B is theory dependent. For example, in two-dimensional conformal field theory, if you have continuous global symmetry, it's automatically upgraded to Kac-Moody algebra. And then B is related to the level of the Kac-Moody algebra. And B prime is just something proportional to B up to some numerical factor given by pi or 2 and those kinds of things. That I'm just writing B prime to brevity of notation. But essentially, in two-dimensional case, it's proportional to K. In higher dimension, it's going to be related to basically the coefficient of some thermal effective field theory. In fact, the coefficient of like Yang-Mills term in low energy effective theory that I will describe later. Did I answer your question?
Yes. Yes.
Okay, thank you. So this is the summary of the results so far. So in both cases, if you take the delta large for fixed representation, the probability of finding particular state in particular representation is proportional to dimension square. But in the case of continuous group, there is a suppression by the second Cauchy. Well, this is actually the leading behavior, leading suppression. And there is actually a subleading term that you can actually calculate, which comes with higher inverse power of delta. So there are higher Cauchy that in principle you can have. But so I'm going to present you a systematic way of calculating these higher moments too later. Okay. So, and this is actually have various interesting implications for when the CFT has ADS gravity dual, then this formula has variety of implications. That was actually the original motivation of me with Daniel Harlow looking into this, that I and Daniel wanted to understand the property of rational Northstone black hole in anti-theta space, and then that leads to this kind of formula. So for example, if you look at this result, we say that supposing, for example, the conformal field theory has Z2 symmetry, which has only 2 elements and only one-dimensional representation, then there is a half chance that you are in non-trivial representation and a half chance, 50% chance that you are in trivial representation. So that means that, for example, if your bulk gravitational theory has fermions in it, then the theory has a fermion number parity. So there is actually almost 50% chance that the large black hole has is fermionic, and there is a 50% chance that the black hole is bosonic. So there is almost, so this has nothing to do with supersymmetry. So even without symmetry, supersymmetry, there is almost a cancellation between fermionic state and bosonic state for any gravitational theory in ADS that contains fermion. So in fact, I just actually last week, at the end of last week, there was a very interesting paper by Yimi Chen and Joaquin Triaci, where they actually studied compare the difference between the partition function of the theory and partition function with insertion -1 to the f for if your theory has fermion in it. And they found that quite a big difference in terms of leading behavior. So this does not explain that numerically, but this actually supports this type of cancellation that they are observing. So this is sort of interesting already, even in that simple level. Okay. So we can also apply similar idea to calculation of entanglement entropy and how entanglement spectrum get decomposed into irreducible representation. So this is a paper that I posted with Yuya Kusuki, Sara Marciano, and Shurdeep Pal last week, actually. So so suppose you have, so this is 1+1 dimensional conformal field theory, but I believe we can generalize it to higher dimension. So the idea is the following. So suppose you have conformal field theory on circle time, 1+1 dimensional conformal field theory on circle times time. Okay, and then you divide a circle into 2 segments, and then you want to calculate the entanglement entropy of the vacuum state, for example. Then according to Omori and Tachikawa, in order to do that, you have to specify the boundary condition at the end of the interval, say A, and its complement. And then, for example, the calculation of Renyi entropy, which is related to the entanglement entropy in the limit of n equal 1, is done by basically calculating this type of annulus partition function with appropriate boundary condition at the end of the entanglement region. Okay, so this is a formula. So Z is this annulus partition function, and I have included this kind of cut by scissor in order to show that, well, this is like consider propagation and then taking trace, etc. Okay, so so this is a standard calculation, but supposing that this conformal field theory has global symmetry G, then you can ask the same question that instead of calculating this trace, we can consider decomposing this open string Hilbert space into irreducible representation, which you can do if you can find a boundary condition which preserves the symmetry. So we assume that we can find a boundary condition which preserves the symmetry, and under the condition, we can repeat this exercise. And then we can actually find a formula like that for both finite group symmetry and continuous symmetry. So this is actually, so Sara is actually a condensed matter physicist and a statistical mechanics expert. And she was a student of actually Pascual Calabrese. So they were working on specific statistical mechanical model and Bess-Witten model to obtain essentially this type of formula. But then when she arrived at Caltech as a postdoc and we were chatting each other, we realized that, well, we can have more general derivation based using similar ideas. So that's how we wrote this paper. So essentially the same idea can be applied to obtain this result. Okay, so this was internal global symmetry, but we can also consider decomposing Hilbert space into space-time representation of space-time symmetry, which means spin in this case. So what you do then is that, again, instead of calculating this type of partition function, we may consider inserting unitary operator implementing now rotation symmetry. So here is this. So L is the angular momentum, and omega is the angular velocity. And so we insert this thing with twist with rotation. This is very similar to, for example, Nekrasov's calculation for omega background, which is why I'm using omega here. And so then we can decompose this into here. So in this calculation, actually, it's important to take into account the Kashmir energy for the ground state for the purpose of later. So we defined Kashmir energy for the sphere to be of this formula, where this is related to the coefficient of the trace anomaly proportional to the Euler density. So in 2 dimensions, this is again related to the central charge, but this is sort of technical side. So let me show you the formula. So this is actually not the most general formula we derived. This is actually for only turning on angular momentum in one direction. We can obtain formula for most general one, but this is what we can derive. We learned later that actually Edgar Chagoulian obtained a similar formula using different approach. But in fact, so we obtained a formula using thermal effective field theory approach. One of the advantages of our approach is that we can actually use that to calculate subleading terms systematically. If we set d equal 2 in this formula, it reduces to the celebrated Cardy formula. If you look at this formula, and you might be puzzled what happened to d equals 3, because there is a d minus 3 in the denominator. But it turns out that when d equals 3, there is a cancellation between here and here, because this is 1 minus d minus 3, and this becomes 1 in d equals 3. So that means that there is a cancellation between these two terms. And so then, in fact, if you take the limit of d equals 3, then this gives you a finite answer. So this actually works in any space-time dimensions. And but I just want to point out again that I'm just for simplicity. Otherwise, it won't fit into this slide. That I'm setting only one angular momentum component to be non-zero. So we have a formula which generalized to most general configuration of angular momentum. Okay, so again, I'm actually summarizing the result for internal symmetry with finite group and compactly group and spin. So these are sort of the result. So finally, one more result I would like to present before explaining how we arrived at it, which is the calculation of three-point function. So spectrum, in the characterizing conformal field theory, the spectrum and the three-point functions are two basic data of conformal field theory. And so we can actually also learn about the behavior of the three-point function in the limit of large energy. In higher dimensions, there is various non-trivial things. For example, unlike the case of two dimension where three-point function is actually a number, in the case of higher dimensions, there is actually conformal blocks for three-point function because rotation group is non-abelian. So and the decomposition of spin contains various different Krebs-Gordon terms. So we have to calculate these partial wave decomposition and the conformal blocks in higher dimensions, of which was actually the main part of this work. And I learned quite a bit about partial wave decomposition and conformal block in higher dimension by working with David Shimon-Zaffen and collaborators. So this is the result. And one of the things I want to point out that in all these formulas, so high energy limit of the partition function with angular density of state with angular momentum, or the three-point function, there is only one number that controls everything, which is this F, which in two dimensions is related to the central charge. And if you have this number, which actually in two dimensions it is related to central charge, so you can calculate it. In high dimension, this is actually a bit difficult quantity to calculate. But if you have this number, then it controls all the high energy behavior of the partition function and three-point function. So this is fairly interesting. I'm going to explain you later why there is such a universality. But here, basically, I'm just telling you the result. Okay, so I have spoken like 20 minutes. And so I presented the result. And if you are interested in, you can stick around and hear how we have arrived at these results. Okay, so basically, there are two ideas. One important concept. One is a Noether theorem and its generalization. And the other is the idea of thermal effective field theory, which I learned from a paper by Shirath Minwara and others. I think there are a variety of various people who have contributed to this idea. So actually, I went to Roberto Longo's 70th birthday party a couple of months ago in Rome, which is a very nice occasion. So this is a paper that actually Edward taught us about this paper, and this was actually very helpful for my work with Daniel Harrow on trying to understand why quantum gravity in ADS doesn't have global symmetry. But so the idea is following. So the standard Noether theorem says that supposing, for example, there is a symmetry, global symmetry in conformal field theory, suppose the symmetry is continuous, like suppose you have Lie group symmetry, then standard Noether theorem says that there is a one-form operator which is conserved. And then if you integrate this one-form operator on the Cauchy surface, then you can actually construct this unitary operator which implements the symmetry. Okay. Oh, I apologize that I was using until now R for irreducible representation, but I realized that here R is actually Cauchy surface, and so I apologize for the confusing notation. And so this here I meant R meant to be the region of the space. So if so in particular because of this form, if the region is the union of disjoint subregions, then this unitary operator automatically becomes a product because it's the integral of the exponential. So this generalized Noether theorem that proven by Buchholz, Duplicia, and Longo basically says that this is true for even for finite group symmetry, provided when you don't have Noether current, provided that the quantum field theory satisfies some fairly general property called splittability. Okay? So if you assume this, you can. So basically, what this means is that even if you don't have Noether current, so that would be a Noether theorem in the strong form. Even if it's not satisfied, it's still true that for some region you can define unitary operators that implement symmetry in the algebra of local operator in that region. And so basically, this was what we used. So we were very, very much grateful for Edward to telling us about this paper. Use this to prove that there is no global symmetry in unshifted space. So that was one concept that is actually was useful in deriving all these formula this time. But the other important thing is this idea of thermal effective field theory. So this is the following idea. So when we talk about effective field theory, we make use of basically the gap in the spectrum. So if the quantum field theory has some very massive particle, then you can consider integrating that out and obtain some low energy effective theory. So that's sort of idea. And here we employ similar idea in analyzing finite temperature relativistic quantum field theory, which is that supposing you have finite temperature, then it's the same as compactifying the theory on the circle times one-dimensional lower space. Okay, and so typically, if you have this kind of situation, then two-point function decays exponentially, because what happens is that if you have two-point functions, there is a thermal disturbance between them, and the correlation function decays. And so this is called thermal mass. And so therefore, there is actually similar kind of mass gap in the low energy effective theory, for theory reduced to d-1 dimensions. So you can consider integrating them out. So in particular, in generic situation where all the state becomes massive and acquire the mass of order of temperature, then if you integrate all the state of the energy level at temperature, then you are left with nothing. There is no propagating degrees of freedom in low energy. So that means that low energy effective theory is actually just a function of the background field. So this is what we assume. So we believe that this is true for generic unitary conformal field theory. There are some examples where this is not true. And the most notable counterexample is a massless scalar particle. So in the case of massless scalar particle, then it is not true, because if you consider massless scalar particle and compactifying it on thermal circle, you still have massless scalar field in one-dimensional lower space. So you are left with one massless degrees of freedom. So in the case of massless field theory, you have to actually include that. So that actually gives you difference from our result. So our results show that actually the behavior, the thermal Hessian function can be expanded in the inverse power of temperature. But in the case of massless scalar field only, to the extent that we have studied, there are terms that are logarithmic in temperature. So that can be explained by the presence of massless degrees of freedom. But in all other cases, I'm aware of that this is a fairly general assumption. For example, for massless fermions, if you compactify on thermal circle, then it is like NS boundary condition, so it acquires mass. And so this is what I assume. So that means that if you want to calculate thermal effective free energy, then you can actually look at, try to construct all possible low energy effective theory terms that satisfy the symmetry, like diffeomorphic symmetries, etc. And then that is turned out to be very sort of powerful method. So then you can ask, well, how we can use this result, this approach to calculate something like this. So Paschen function with insertion of u of g. Well, if we are just calculating partial function, we will be calculating basically the grand, the partial function in the geometry where you are compactifying the things on the circle. But if you insert u of g, then what happens is that if you go around the circle, then there is the action of g. So that means that you are considering non-trivial g bundle on the circle. So we are turning on something like a gauge field, flat gauge field around the circle, which in the case of Karuta-Klein, in the context of Karuta-Klein compactification on the circle, is the same as in turning on the scalar field that was obtained by, so if you have gauge field, Abelian gauge field, say, on the circle times d minus 1 dimensional space, then from the point of after Karuta-Klein reduction in d minus 1 dimensional space, you have a gauge field and scalar field in the adjoint representation. So turning on G means that it gives you the web for this adjoint scalar field by G. So end result is that the leading term in the low energy effective theory is proportional to t to the d minus 1, but can be a function of which depends on the group element that depend on this scalar field in the adjoint representation. And here I have written dot, dot, dot. And these dot, dot, dot are like, say, for example, kinetic term for this scalar field or the field strength square of the gauge field, etc. And those are suppressed by 1 over t. So this is the leading term that you can write down. And this depends only on V of G. Okay? So if we calculate V of G, then we can understand the leading behavior of the free energy. Now, I would like to argue that this V of G is actually related to the tension of the domain wall, which implement this symmetry. So this can be argued in the following way. So let me first mention this. So I wrote this thermal effective field theory. So in particular, if you consider flat geometry of S1 times d minus 1 dimensional space, and if you take G to be constant, then we will be on the left-hand side, we will be calculating this partial function. And on the right-hand side, we just insert G to be, we just assume G to be constant. And then what you obtain is that you have T to the D minus 1 and V of G times the volume of the Cauchy surface times the original partial function. Okay, so therefore, if we calculate this, we'll be calculating what we want to obtain. So now I would like to argue that V of G is the tension of the domain wall. And the idea is the following. So when we write this low energy effective theory, the reason we can write it in this way is that since all the particles get the mass of order of temperature, for high temperature limit, that there is only contact interactions. So therefore, global topology is not relevant to the leading term in the low energy effective theory. And all the geometric information on the Cauchy surface is actually included in this term. As far as you write the low energy effective theory terms in a way that is diffeomorphic invariant, then there is no other geometric information we need to incorporate. So this is great. So this means that we can actually choose any Cauchy surface we like, that and then use the calculation. So for example, in particular, we can so here there is already thermal circle, but we can choose the d minus 1 dimensional space to be another circle times d minus 2 dimensional space. So we can assume that there are actually two circles in the geometry. So once you have two circles, then we can use a standard trick that we are very familiar in 2 dimensions, which is to swap these two circles. And then what you get by doing that is that previously, if you consider this theta, this S1 of beta to be thermal circle, then what this red thing is implementing is a twist around this. But if your Cauchy surface as extra circle, and if you actually interchange the role of these two circles, regarding this as thermal circle, and regarding this as a part of the Cauchy surface, then what this operator U of G is now doing, so you have this topological operator, but what this topological operator is doing is to implementing the action of G on the Cauchy surface, and that is the same as the domain wall. And we can actually look at the power of these things and propose various coefficients. And you can see that actually V of G scales exactly like the domain wall tension, because you have T to the D minus 1, which you can write as T times t to the d minus 2 times the v. But t is actually the length of this circle now after rescaling everything by temperature. And this is the volume of this remainder of Cauchy surface after rescaling. And then you have a domain wall tension. So you can interpret it as domain wall tension. So domain wall tension is actually a non-negative, has to be non-negative, which you can actually easily argue. And if we can prove that the domain wall tension is strictly positive for non-zero G, then this is actually what we want to show. And in fact, Shurdeep Par and J.D. Song and Johan Zhang, three of us with me, is actually working using this generalized Nater theorem to try to prove this. And so this we are trying to write up very soon. And so assuming this, what we can say is that since now, so what this means is that since V of G is a tension of the domain wall, so it has an absolute global minimum for trivial G, and otherwise it is positive. And if it is so, then this would go to 0 when G is non-trivial, and it's going to 1 when G is trivial, because when G equals 0, then V of G is 0. And so therefore, we obtain this formula. Now, by using this formula that we all learn in undergraduate course on mathematical method of physics, that Kronecker delta in group manifold can be decomposed in terms of character in this way, then we arrived at this formula. So basically, this is the sort of idea. So the important thing is that using this summary effective field theory, we can relate the calculation insertion of U of G to the, and in particular this term Bg, to the tension of the domain. We can repeat this exercise for a compact Lie group. So in that case, we have to actually include some sub-leading terms. And then, so this is, and then we can repeat this exercise. But then if you include this sub-leading term, and we can relate this to the Katsumudi, in the case of two-dimensional, we can relate to the level of Katsumudi algebra, then we arrived at this formula. So if there is a nice way to derive this formula, which is to notice that this quantity actually satisfies the heat equation on the group manifold. And so there are actually two ways to write a solution to heat equation. One is in terms of Gaussian, and the other is in terms of sum of a character, but weighted by the second Casimir of the character. So there are two ways of writing the solution to heat equation. And by comparing this, we can actually derive this result, which leads to this result. Okay, so this is sort of this is a result for the case of compact group, and it's interesting to actually work out some example to see how it actually works. So for example, for free massless scalar field, we can calculate this, and then we can actually check this number. For free fermion, we can also calculate this. I mentioned that the assumption we used in deriving this, that is that in the thermal effective field theory, there is no degrees of freedom because of thermal mass, is not true for massless scalar. And in fact, we can see the deviation from this formula for d equals 3. So in the case of d equals 3, actually leading term contains logarithm. And that is actually, I think the reason for this, I believe, is that the assumption in arriving at this formula is actually not true in the case of massless scalar. For this dimension greater than 4, actually leading term is not affected somehow. It's also interesting to work out a holographic example. So in this case, the calculation we should do is holographic dual of this calculation is a Reissner-Nordström solution. So we can consider calculating Reissner-Nordström generalization of the charged black hole, generalization of Reissner-Nordström black hole for non-abelian group. So what you consider is that in the bulk, you have Einstein-Hilbert term, and you have Yang-Mills theory of group G. So when we were writing this paper, we went through some general relativity literature in the late 90s and early 20s. and try to see whether these people have calculated the free energy, the entropy of charged black hole for non-abelian group. So to our surprise, actually, it turns out that there was an unsolved question about the thermodynamic behavior of non-abelian black hole, and this was posed as a puzzle. So the puzzle was the following. So there are actually two candidates for non-abelian black hole. So one is actually simple one, which is to notice that this is a class function. So that means that we can conjugate G so that it goes to maximum torus. So if G is in maximum torus, then you can pretend that this non-abelian group is actually a bunch of U1 abelian group, U1 to the R, where R is a rank of gauge group. And you can just consider standard abelian rational Nordstrom solution with abelian gauge field in the U1 to the rank of G. And then you can actually calculate the entropy of that black hole. And but then there is also a genuinely non-abelian solution that those people found. And there is actually a couple of very nice review articles that we studied. And but the general relativity theorists could not figure out which one is more stable. So we were puzzled which one we should look at. By the way, they were looking at asymptotically ADS, charged black hole solution in this context. And then there was this question. So actually, we actually understood how to think about it. And so the idea is the following. So we are interested in actually very high temperature limit, which in ADS is a very large black hole. So in the limit of very large black hole, near the boundary, all the field becomes exponentially decayed. So the difference between these solutions, so we guess that difference between these solutions disappears in the limit of high temperature because all the field decay exponentially. So therefore, no abelian interaction becomes negligible. So therefore, the difference between these solutions should be negligible. And we actually checked that if I look at their solution and evaluate that numerically and go to high temperature limit, they become identical solution. So we can start from there and then go to a lower temperature and see how the partition function deviate from each other. And we actually found that the genuinely no abelian solution has thermodynamically more stable. That is that it has bigger entropy and smaller free energy. So this is the preferred solution, and then we can actually use that to calculate these coefficients. Okay? So that's what we did, and so again we can. So this is changing story a little bit, changing direction a little bit. We can also do this entanglement entropy calculation. So we also, so more recently, David Simon-Zaffen, Nathan Benjamin, and Jaiha Lee, and I actually applies a similar idea to understand now decomposition of Hilbert space in representation of space-time symmetry. So what we did is this. I guess we have maybe 5 or more minutes, so maybe I can show you some of my note. So I apologize for my handwriting, but what we did was that you consider CFT in S1 times some Cauchy surface, and then we make this CALTECH line ansatz, and then we substitute this into this, and then low energy theory and expand, and we calculate these coefficients. That's what we did. But we are interested in doing that when this S1 is twisted, because this, just like in 2-dimensional conformity theory calculation, where if you turn on angular velocity, we are considering this slanted parallelogram. So similarly, this is twisted like that. So then we need to calculate this coefficient, that lower dimensional metric and gauge field, etc., CALTECH line gauge field. In this case, in this setup, and then we can actually calculate these things, and this is the result. This is essentially very similar to the calculation that Nekrasov did in his omega background calculation. And the interesting thing is that you have this denominator 1 plus omega square times something, where omega is angular velocity. And so this actually, after doing this integral in the Cauchy surface, on the Cauchy surface, this gives rise to this denominator. So in particular, what this is interesting is that when the angular velocity becomes I or minus I, there is a pole. And so this pole has various interesting consequences. And so we can use that to go to actually very high angular momentum as well as high energy. And we cannot quite get to the light cone limit. I would have liked to go to the light cone limit and compare the result to the light cone CFT calculation. But that was not the limit this method allows. So anyway, so that leads to this kind of formula. Okay, so this leads to this higher dimensional version of the CADI formula. So again, here I'm summarizing these results. So finally, I would like to present to you the result of the calculation of the 3-point function. So in this case, what we did is actually generalization of a 2-dimensional CFT calculation. So let me actually again go to my note. So let's see if I can. Oh yeah, here it is. So there is actually an earlier work by John Carty and Alexei Maloney and Henry Maxfield, and also Scott Collier and Alex, etc., where they did a 2-dimensional version of the calculation. So what they did was to consider genus 2-dimensional conformal field theory on genus 2 Riemann surface, and consider the limit when so genus 2 Riemann surface can be considered as a sphere with 3 disks removed, and then connected by cylinders. But you can take the limit when cylinder becomes very thick. So in that limit, lots of very high temperature states are propagating. And they evaluated this limit and calculated the behavior. And they obtained some interesting results. So basically, David and my collaborators wanted to do similar thing in high dimension. So we basically generalized the Schottky parametrization of the 2-dimensional genus 2 Riemann surface to higher dimension. So instead of a 2-dimensional sphere, we consider a D-dimensional sphere or D-dimensional flat space, and then remove the 3 balls and glue them by 3 D-dimensional cylinder, and then do the calculation. And the non-trivial step is to work out the conformal block decomposition for this higher dimensional version of Schottky parametrization. So there actually the group theory helps a lot. So basically you can glue these 2 cylinders together by using element of a conformal group in Euclidean space. And so you can think of this as a conformal block as a function of 3 elements of conformal group in higher dimension. And then you can use group theory of this conformal group to parameterize, to find the appropriate basis for conformal blocks. Conformal blocks are basically solution to Casimir equation on the group manifold. And so that's we use for this decomposition. So okay, so again, so the interesting thing in this calculation is that the high temperature limit is the limit when the length of this cylinder becomes very short. And so when the length of the cylinder becomes very short, there are particular cycles on this geometry where the length of the cycle becomes very small. That is that, for example, there is this point where 2 spheres, 2 boundaries of the disks are touching each other. And that is where, in the limit of beta goes to 0, that is where the effective temperature becomes very high. So there are actually places where what we call hotspot, where the temperature becomes very high. And so then we can sort of collect contribution from this hotspot. And so that's sort of, that's why actually the same universal coefficient. So I pointed out earlier that for both high temperature behavior, high energy behavior of partition function, and high energy behavior of 3-point function, the same coefficient F appears. And the reason for this is that everything that controls this high energy behavior is actually this leading term in the thermal effective field theory. And that is basically the cosmological constant in thermal effective field theory. And that controls all these terms, and then that's how we obtained this result. So basically, that's all I wanted to say. The organizer reserved 10 minutes for Q&A, and so I'd like to end. So I this is basically the summary of the result. And the summary effective field theory, just like other effective field theory, is like a telescope. So we can actually look at this very high energy behavior by using this seemingly in the opposite limit, where we consider low energy effective action, but by integrating out all the high energy degrees of freedom. And that turned out to be very powerful method and enables us to obtain this variety of universal behavior of quantum field theory, high dimension. So that's all I wanted to say. Thank you very much for your attention.